So the last topic in this first unit is moment generating function. So what is this moment generating function, right? So before going to the moment generating function, first we have to discuss what is a moment here. So in physics might be you have learned about the moment, that is nothing but force of inertia and all, right? But here statistically this moment generating function is different, right? So we are finding the moment of the function here. If the moment of the function exists, then from there you can calculate the different characteristics of that function here, right? So we use this moment generating function in the electrical part, right? So there if the circuit works for particular limit, right, then is the circuit accepting more power or not, that can be found using this moment generating function. So this moment generating function is denoted by mx of t and it is given by expectation of e power tx, where here t is a real constant and x is a random variable. Now when x is a random variable, it can be a continuous or it can be a discrete. So when x is a discrete, it is given as summation e power tx into p of x. When x is discrete random variable, and when x is continuous, integral e power tx into the corresponding density function f of x dx when x is continuous random variables. So this can be found using moments, right? So moments are classified into two types as raw moments and central moments. So using these raw and central moments, we can find the different characteristics of a function. So this raw moment is also known as moment about the origin, right? And it is denoted by mu r dash. And it is given by the formula expectation of x minus 0 whole power r, since they are defined from the origin, or simply you can write it as expectation of x power r here, right? Whereas the central moments are denoted by mu r, and the other name for central moments is moments from the mean. From the mean means again e of x. So it is given by expectation of x minus x bar whole power r, or else instead of x bar you can write e of x also, right? So there is a relation between these two also, but before going to that, just we have to know the first four or first three moments of this, right? For let us consider the raw moments here. So when here x equal to, when here r equal to 0, then it is called the zeroth raw moment, which is always equal to 1. That means expectation of x power 0, right? X power 0, anything power 0 is 1, and expectation of constant is constant, expectation of 1 is 1 here. But when r equal to 1, that is mu 1 dash, it is nothing but expectation of x here, right? That means expectation of x power 1 is x only. So this expectation of x is nothing but the mean. So the first raw moment is known as the mean of the random variable. Then mu 2 dash, that means if r equal to 2, it is expectation of x square. Okay, that's what we are finding in the variance, right? Expectation of x square is nothing but the second raw moment. Similarly here, like that, if you take r equal to 3, it is expectation of x cube mu 3 dash, r equal to 4, expectation of x power 4 mu 4 dash, right? If you consider the central moments, so in central moments, right, if r equal to 0, that means here mu 0, right, expectation of x minus x bar whole power 0 is 1. The zeroth central moment and also the zeroth raw moment are always equal to 1 here. Next, if r equal to 1, then mu 1 is equal to expectation of x minus x bar whole power 1 here. If we apply the expectations, expectation of x minus expectation of x bar is mean, means a numeric value is x bar. But again expectation of x can be written as x bar. So x bar minus x bar is 0. So, therefore, mu1 is equal to 0. So, the first central moment is always 0, but the first raw moment is always the mean. Okay. Next, if r equal to 2, that means mu2 is equal to expectation of x minus x bar whole square, right. So, this is nothing but the formula for variance, because x bar is nothing but here expectation of x. X bar is expectation of x here. So, it is variance of x. So, the second central moment is variance of x and the second raw moment is expectation of x square. And also we can have a relation between the raw and central moments, right. Like we can represent this mu2 as mu2 dash minus mu1 dash whole square. That is mu2 dash is expectation of x square and mu1 dash is expectation of x, which is nothing but the formula for variance of x. Okay. So, this is about the moments. Now, we have a properties for moment generating function, because from this moment generating function we can derive the density function for a given distribution function also. So, if we consider the t is a real constant and here x is a random variable, then the first property is here mx of 0 equal to 1, right. So, by definition what is mx of t here? Expectation of e power tx here, right. But if that is t is 0, 0 into anything is 0, e power 0 is 1 here. So, expectation of 0 into x in place of t, right. So, it is expectation of 1 is 1. Similarly, if we consider c is any arbitrary constant, again I have defined in the previous classes, arbitrary means the sudden occurrence of the experiment, right. Then mcx of t is equal to mx of ct, because the arbitrary constant it has also some value. Then if we consider x1, x2 and so on xn as n independent random variables, then here mx1 plus x2 plus so on xn of t is given by mx1 of t, mx2 of t and so on mxn of t here. Okay. And the last property is that here we can obtain the density function, right. So, that can be obtained by using the raw moments here. So, mu r dash is given as dou power r mxt by dou t power r at t equal to 0, right. So, whatever is the moment generating function is there, if we differentiate this with respect to t, right, e power tx by t, right, then again differentiate that e power tx by t square like that. So, and there if you just put t equal to 0, you will get the raw moments mu r dash. If r equal to 0 here, right, mu 0 dash, so there you will get the mu 0 dash value. And if r equal to here 1, so here you just differentiate this with respect to 1 time, right, dou mxt by dou t, right. If r equal to 2, then differentiate this moment generating function with 2 times, that is dou square mxt by dou t square. So, in this way we can find the different characteristics of a generating function of random variable. Let us see the problem on moment generating function. If the density function is x for 0 less than x less than 1 and 2 minus x for 1 less than or equal to x less than 2, we have to find the moment generating function. So, here x is a continuous random variable and it is defined in 2 intervals here, right. So, by definition here moment generating function is mx of t equal to integral e power tx into f of x dx. Why? Because here x is a continuous random variable, right. Now, here x is taking the 2 intervals. So, integral over 0 to 1 e power tx into f of x dx plus integral over 1 to 2 e power tx into f of x dx. Now, integral 0 to 1 means from 0 to 1 the density function is given as x here. So, 0 to 1 e power tx into x dx plus now 1 to 2 the function is 2 minus x into e power tx dx. Now, integrate this. Again consider x as u and e power tx as v here. So, x into e power tx by t minus differentiation of x is 1 and integral e power tx by t is e power tx by t square from the limits 0 to 1 plus, now here consider 2 minus x as u and e power tx as v here. So, 2 minus x into integration of e power tx is e power tx by t minus, now differentiation of 2 minus x, 2 is 0 and minus x is minus 1. So, minus 1 into e power tx by t square from 1 to 2. Okay. Now, if you apply the limits here, it is here, if you apply the upper limit, 1 into e power t into 1 is t. So, e power t by t minus t into 1 is again t. So, e power t by t square. For lower limit, you have to take minus sign before. If x is 0, so this term becomes 0, and here if x is 0, t into 0 is 0, e power 0 is 1. So, 0 minus 1 by t square, right. So, this is the about the 0 to 1. Now, let us consider the limits of 1 to 2 here. So, plus, if x equal to 2, right, 2 minus 2, 0, 0 into anything is 0, minus, minus minus becomes plus, e power 2 into t, 2t by t square. So, e power 2t by t square minus of lower limit. If x equal to 1, 2 minus 1 is 1, e power t into 1 is e power t. So, e power t by t minus minus becomes plus, e power t into 1 is t by t square. Now, simplify this. So, e power t by t minus e power t by t square minus minus becomes plus 1 by t square, and here e power 2t by t square minus e power t by t minus e power t by t square. So, here e power t by t and minus e power t by t will get cancelled, right. So, here minus e power t by t square minus e power t by t square, right. So, this can be written as minus 2 into e power t by t square plus 1 by t square plus e power 2t by t square. So, take out here denominator common. If you rearrange the terms here, it is e power 2t plus 1 minus 2 e power t, right. If you see here, it is nothing but e power t minus 1 whole square, because e power t whole square is e power 2t plus 1 whole square is 1 minus 2ab, that is minus 2 e power t. So, this is e power t minus 1 whole square by t square. Again, this can be written as e power t minus 1 by t whole square. So, the moment generating function of this density function is e power t minus 1 by t whole square. The next problem is moment generating function. If the moment generating function is 2 by 2 minus t, then find the variance of x. So, this we have to obtain using the density function, means we have to differentiate that, right. So, moment generating function is given as 2 by 2 minus t. So, let us first simplify this part here. So, in the denominator, if you take here 2 common, it is 1 minus t by 2, right. Now, this 2 and this 2 will get cancelled. So, this is 1 by 1 minus t by 2, which can be written as 1 minus t by 2 whole power minus 1, right. So, this is the moment generating function. Now, for this we have to find the variance. Now, differentiate this moment generating function with respect to t partially. So, dou m of t by dou t. Okay. So, differentiation of this is minus 1 into 1 minus t by 2, inner derivative of t by 2 is minus 1 by 2, and here it is minus 2, power is here minus 2. So, if you simplify this, minus 1 into minus 1 by 2 is 1 by 2 into 1 minus t by 2 whole power minus 2, right. Now, we have to find the variance, that means we have to find in terms of moment mu 2. So, we have to differentiate this again, right. Then this becomes here dou square m of t by dou t square, right. So, 1 by 2 is constant, so this will be like this only. Now differentiation of 1 minus t by 2 whole power minus 2. So this becomes minus 2 into 1 minus t by 2 minus 3 into the inner differentiation is minus 1 by 2. So if you simplify this here, this 2 will get cancelled, but minus 1 into minus 1 by 2 is 1 by 2 into 1 minus t by 2 whole power minus 3. This is your dou square m of t by dou t square. Now, if here t equal to 0 in dou m of t by dou t, right, then this becomes mu 1 dash, right. So, mu 1 dash equal to, what is dou m of t by dou t here? 1 by 2 into 1 minus t by 2 whole power minus 2. So, 1 by 2, 1 minus t by 2 whole power minus 2 at t equal to 0. T equal to 0 means 0 by 2 is 0, 1 minus 0 is 1, 1 power anything is 1. So, mu 1 dash is equal to 1 by 2, right. Then again consider t equal to 0 in dou square m of t by dou t square. Then this becomes mu 2 dash equal to, what is dou square m of t here? 1 by 2 into 1 minus t by 2 whole power minus 3 at t equal to 0. So again if you substitute here t equal to 0, it is how much? 0. So 1 power of minus 3, right. So this is again 1 only. So 1 by 2, that is your mu 2 dash. Now variance in terms of moment is given as mu 2, that is mu 2 dash minus mu 1 dash whole square. What is mu 2 dash here? 1 by 2 minus, what is mu 1 dash? 1 by 2 whole square. It is nothing but 1 by 2 minus 1 by 4, which is again 1 by 4. So therefore the variance is here 1 by 4. So like this we can obtain the mean and variance of the moment